So what we're going to look at with these additional notes, some of it will be review, some of it will be some minor details that will add to details that we already know, and some of it will be some new strategies that we're going to use for permutations. Now, permutations, combinations is part of a branch of mathematics called combinatorics, and that's just a fancy word for counting. And so we're going to be looking at some more of these kind of questions. We already looked at the fundamental counting principle. This was our first strategy. This strategy is where we drew a line for every decision that we needed to make and then put our number of choices. So here you have a new car and the owner has 3 choices. So how many decisions does this owner have to make? 3 decisions. Needs to make a decision for color, transmission, and interior. So again, just a little brief explanation underneath your spaces to describe what that decision is, and then you can put your choices in there. 3 choices for color, 2 for transmissions, 2 for interior. That gives you a total of 12 different ways. Of course, you could do this with a tree diagram as well, but the fundamental counting principle is the fastest way to do it, with showing the least amount of work. Sometimes we're given numbers and we're allowed to repeat the numbers, use them as many times as we'd like, and sometimes it's a permutation where it says this is a list of objects and you can only use one once. So if you were making a 3-digit number, you'd have 3 decisions to make. And if you were allowed to use the 7 digits 1 through 7 and repeat them, well then this could be 7 choices here, 7 choices here, 7 choices here, for 343 total choices. Oh no, that's without repetition. Whoa, here we go. I read them wrong. Let's just move this over there. Perfect. And without repetition, well, then you'd still have 7 choices for the first one, but one of those numbers would be used up. We don't know which one. One of those would be used up. Then there'd only be 6 left for the second one and 5 left for the third one. And so when you're not allowed to repeat the numbers, another way that you could write this is 7p3. It's a permutation because we have a certain number of objects and we're arranging a certain amount of them in an order, and this time the amount that we're arranging is 3 of them, and we start with the number 7. Now we haven't looked at restriction questions yet, so this is a small addition to the strategies that we've had so far, but sometimes we've got a restriction. So again, for example 3, we're still going to use the numbers 1 to 7. And the question says, how many 3-digit numbers are even without repetition? So we're allowed to use the numbers 1 through 7. Once you use a number up, it's used up, and it has to be even. Now the strategy is written here for you. Our strategy is we have to deal with our restriction first. So when we look at this, if we didn't deal, the restriction is here on the end. This one has to be even. So first we'll do it right. If we deal with the restriction first, and that number is even, how many choices do we have for that last space? 3, because it can be 2, 4, or 6. So with your restriction, again, here it's where it's sometimes nice to be really detailed in your description underneath. I said it's even, and I even wrote which possible numbers it could be, 2, 4, or 6. Then how many choices do we have here? Because these last ones don't have restrictions on them. We have 6. Why is it 6? Well, there was 7 numbers to begin with, but we've used up something. We've used up either the 2, the 4, or the 6. So if you used up the 2, how many numbers would be left? 6 numbers. If you used up the 4, how many numbers are left? 6 numbers. If you used up the 6, how many numbers are left? 6 numbers. And now for our last one, we've used up 2 numbers. How many choices would we have for our last decision? We'd have 5. This gives us 90 in total. Now what's hard is we're students, we like to write numbers from left to right. We like to start with our first number. So what happens if we didn't deal with the restriction first? Well, we still know this has to be even, but if we started with the first space, because there's no restrictions, how many choices do we have for that? 7. So we put 7 in there. And then how many choices do we have here? 6. So we put 6 in there. But now we run into a problem. Because I don't know what number to put in here. I want to put 3, right? Because this could be a 2, a 4, or a 6. But can you see that when I say I choose any number for my first one, any of the 7, I might have used up my 2. So maybe I should put 2 here. But I might not have used up my 2. Oh. So I get into a problem. Because this number could be 3, or it could be 2, or it could be 1 if I happen to use a 2 and a 4 up already. So this is why things don't work out. But if we start with our restriction, if we say I'm going to put either a 2, a 4, or a 6 in my last digit first, whichever ones I don't use up get put back into our 6 and our 5. So when we're dealing with a restriction, we have to deal with that restriction first. So I want you to try, again, just using the numbers 1 through 7. I want you to try how many are odd. And after you get your answer using one method, I want to see if you can think of another method to get that same answer. So my guess is most of you did this strategy first. You wrote odd here. You said there's 1, 3, 5, or 7 are my odd numbers, giving me 4 choices. Now I've used up a number. I only have 6 choices left here and 5 choices left there, leaving me with 120. So that's the first strategy. That's the main strategy most of you would have used because we just did that strategy before in the example before. Can anyone see another way to figure out that this would be 120? You might have to look back a little bit further in our notes, back to example 2. That's the hint. What did we find in example 2? Did we figure out that all of them, if you weren't allowed to repeat, was, no, not 120, sorry, 210? Is that what we found? 7 times 6 times 5? And if we had 210 for all of them, and we figured out in example 3 that there was 90 even ones, how can we figure out how many odd ones there's going to be? You'd have to subtract. And if you took the 210 and subtracted all the even ones, we would be left with all the odd ones, leaving us with 120. We're going to use this strategy as well. This is, I call this the not strategy, where you count what you're not supposed to and subtract those bad ones from all of them, and you'll get what you want to count. Now, in this case, it's just as easy to count the ones you want directly, so that's fine. But we will get some cases where what we want to count directly is hard to count, but counting what's bad and counting all of them is going to be easier. So we'll see that in some examples coming up. but I thought I'd introduce the strategy a little bit already. So now we want a 3-digit number. We want to use the numbers 0 through 9 without repetition, so you're not allowed to repeat a number. How many can be done? Okay, I'm going to give you a start on this. Did you find the restriction on this one? It's a 3-digit number. On one of these digits, there's a restriction. Where is that restriction? The first one. What is the restriction on the first one? It can't be 0. So this is not 0. So how many choices do we have for that first digit? 9. Now how many choices do we have for the second digit? Now you have to be careful because we get used to writing 987, so you might have been tempted to do that, 987. But now you've used up one number, but 0 goes back in. We still have 9 choices there. And then 8. So this is 648 different numbers that have 3 digits where all the digits are different. Which, if you think about how long that took to do, it wasn't that long. But before you had these strategies, if someone said, how many numbers are there between 100 and 999 that don't have any numbers that repeat? Oh, you'd start, okay, well, first one would be 123, and then 124, and you start listing them. That would take a long time. And then once you've listed all 648 of them, you'd have to count them up and hope you didn't miss one or accidentally write another one. Any questions so far? Yes. Well, if it was 0, I think that is 27, and that would be considered a 2-digit number. Now, we have to be careful with this because sometimes you'll get questions that instead of saying numbers, okay, because this is a 2-digit number, it might say codes, right? You know, your code to get into your garage is a 3-digit thing you punch into a keypad. Well, then 0 to start off with would be okay, because then you could have a code that is 00000. But it's not, as a number, that's not a 4-digit number or a 3-digit number. Quick review of factorial notation, mental math. 42, right? Because if we expand the bigger one, we get to 5 factorial, which cancels out with the 5 factorial on the bottom, leaving us with 42. This one's a little bit more work. Start expanding the bigger one until you get to 1 on the bottom. I'm going to write the 4 factorial as 4 times 3 times 2 times 1. Are you okay if I cancel out this 8 with the 4 and the 2? Are you okay if I cancel out the 3 and the 9 and leave a 3 on top? Because 9 divided by 3 is 3. Now, mental math, if I was multiplying that, what am I left with? I'm left with a 10, a 3, and a 7. 7 times 3 is 21 times 10, 210. And then when you get to variables, again, we decide which one's bigger, n plus 2 or n. N plus 2 is bigger. So we start expanding the bigger one until we get to the one that's on the bottom. And we're just left with n plus 2 times n plus 1.